Good morning, students. Theory of estimation, part 2. Second criteria of the good estimator, consistency, is very another important property of the theory of estimation. An estimator, TN, function of sample observations, x1 is to xn, based on a random sample of size n, is said to be consistent estimator of g of theta, function of theta. Theta belongs to parametric space. Already explained. Circle, H circle is a parametric space. The theta is a part of the parametric space. If Tn converges to g of theta in probability, convergence probability is a advanced probability technique, is a modern probability concept. So here we have defined the convergence to g of theta in probability. That is the notation of convergence. Tn is read as converges to in probability g of theta as n tends to infinity. Tn is converges in probability to g of theta. Tn is said to be consistent estimator of g of theta. So this is a very important concept. Now alternatively, so we have important remarks here. Using Chebyshev inequality, easily we can identifying the function of sample observation, which is a consistent estimator of g of theta. That estimator Tn is said to be consistent if probability of modulus Tn minus g of theta less than epsilon. Epsilon and here is this is theta, positive, smallest positive real numbers, the less than epsilon greater than 1 minus theta for every n greater than equal to m. So a sample size is greater than equal to m. Alternatively, the probability of modulus t minus g of theta, t is a statistic less than epsilon tends to 1 as n tends to infinity. T is said to be consistent estimator of g of theta. Consistency is a limiting property of estimators. Consistency is a limiting property of estimators. Summation xi by n minus 1, summation xi by n minus 2 are all consistent estimator of population mean mu. So now this summation xi by n is converges to mu. Summation xi by n minus 1 is converges to mu. Summation xi by n minus 2 converges to mu. Converges in probability. So now here is the limiting property of estimators. Example, sample mean x bar 1 by n summation xi by using Kinchin's law of Kinchin's laws by Chebyshev inequalities converges in probabilities. So summation xi by n is a x bar. Summation expectation of xi is existent. So now here is we can able to write this one. Summation xi converges in probability e of xi. E of xi is equal to mu as n tends to infinity. So this summation is tends to mu when converges in probability. So now x bar is what? This is x bar is always consistent estimator of population mean mu. The population follows normal distribution mu comma sigma square. So we have very important property of consistent estimators. Invariance property of consistent estimator is very powerful property. Tn is a consistent estimator of g of theta. Tn converges in probability to g of theta. F of g of theta is a continuous function, like as a sine of log x, e power x square, e power minus x square, root of x square plus 4x is a continuous function of g of theta. F of g of theta is a continuous function of g of theta. Then f of t of n is a consistent estimator of f of g of theta. For example, x bar is a consistent estimator. X bar is a consistent estimator, converges in probability mu. So by using this property, x bar square, the function of x bar, f of g of theta, is a continuous function. X bar square is a continuous function. Converges in probability mu square. It's very, very powerful property, invariance property. F of t is a consistent estimator of f of g of theta. It's very, very important property. Sufficient condition for consistency. Another alternative way to identify the consistent estimators of the unknown population parameters, unknown population characteristics. So this sufficient conditions for consistency is very, very important concept. Easily we can identify the function of sample observations and write the consistent estimate, give the consistent estimate of the unknown population parameter theta. Let Tn be a sequence of estimators such that all theta belongs to parametric space. Expectation of Tn tends to g of theta as n tends to infinity. Limit of n tends to infinity, expectation of statistic tends to g of theta. So first condition. Second condition, variance of Tn tends to 0 as n tends to infinity. Therefore, Tn is a consistent estimator of g of theta. These two satisfied, these two conditions satisfied. So we can say that Tn is a consistent estimator of g of theta. Now, for understanding purpose of these consistent estimators, so we have to take some examples. Examples are very, very important for the examination point of view. All examples are very standard results. Example 1. Example 1. Let xi follows n of mu comma sigma square. I is equal to 1 to and so on n. Consistent estimator of mu and sigma square dash. Solution. We know that sampling distribution of a statistic sample mean follows normal distribution x bar n of mu comma sigma square by n. So E of x bar is equal to mu from this one. Variance of x bar is equal to sigma square by n. As by applying sufficient condition for consistency, already explained, as n tends to infinity, expectation of x bar is equal to mu. Variance of x bar is equal to sigma square by n. So variance of x bar tends to 0. Variance of x bar tends to 0 as n tends to infinity. So now sufficient condition for consistency is satisfied. Therefore, x bar is consistent estimator of population mean mu, unknown population mean mu. Next, for large n, so now here the expectation of x square is equal to sigma square for large n, asymptotically unbiased estimator. Small s square is a asymptotically unbiased estimator. Expectation of small s square actually n minus 1 by n sigma square. Expectation of s square is equal to 1 minus 1 by n sigma square. Variance of s square is equal to the formula is 2 sigma power 4 by n. So now limit n tends to infinity. Expectation of s square is equal to limit n tends to infinity. So 1 minus 1 by n, 1 minus 1 by n, 1 minus 1 by n sigma square, that is equal to, as n tends to infinity, this is equal to sigma square. Therefore, expectation of s square is equal to sigma square. Now, second one, limit n tends to infinity, variance of s square is equal to limit n tends to infinity 2 sigma power 4 by n. So now this value tends to, as n tends to infinity, this value is 0. Therefore, so sufficient conditions for consistency satisfied. Therefore, small s square is consistent estimator of sigma square. Consistent estimator of sigma square. So problem one is very, very important here. Example, suitable example for understanding purpose of the consistent estimator. One more example. Example 2. Let x1, x2, and so on xn be a random sample. Of observations, random sample of observations from a population with probability function p of x equal to 1 by n, x equal to 1, 2, 3, and so on n. This here is x follows discrete uniform distribution. X follows discrete uniform distribution. Parameter is Kaplan. So we have to give the consistent estimator on this one. So now here, what is the mean? So to identify the consistent estimator of Kaplan, first of all, you have to calculate the mean here. Expectation of x equal to, by using the properties of discrete uniform distribution, n plus 1 by 2. Variance of x is equal to n square minus 1 by 12. So refer the video lessons, discrete probability distributions. These two are the very, very important properties of uniform distribution. Here is from this population, and finite size of random sample is drawn here. X1, X2, Xn is drawn from this one. So identify this function, the suitable function, that is called a statistic. The suitable function in general, expectation of x bar. So by thumb rule, E of x is same as to E of x bar. Now here is n plus 1 by 2. Here variance of x bar is formula sigma square by n, sigma square by n, sigma square by n, sigma square by sample size n, sigma square by n. Here is sigma square is n square minus 1 by 12n by simple technique. So directly we can calculate the E of x bar and variance of x bar. So replace x bar by summation xi by n, summation xi by n, already explained in the previous videos here. So here is directly you have to able to write the so E of x bar and variance of x bar by using the formulas, not procedure. So now here limit n tends to infinity, expectation of x bar, expectation of x bar. 1 minute here. Before taking this one here, first of all, we have to unbiased estimator here by cross multiplication. 2x bar is equal to n plus 1 implies expectation of 2x bar minus 1 is equal to Kaplan. Is equal to Kaplan. Now, similarly here, variance of 2x bar minus 1, we have to calculate this one also. With the help of the previous information. So now apply the variance property. 4 into variance of x bar. Variance of constant is constant. Variance of constant is 0. So variance of ax is equal to a square into variance of x. 4 into n square minus 1 by 12n into 12n. Here is 12n here. 12n. So now by simplification, 4 3 times cancel. So n square minus 1 by 3n. N square minus 1 by 3n. Now here apply the sufficient condition for consistency and identify the consistent estimator of the parameter Kaplan. Limit small n tends to infinity. Expectation of Ux bar minus 1. So independent of small n, this value is equal to n. Limit small n tends to infinity. Variance of Ux bar minus 1. Limit of small n tends to infinity, that is n square minus 1 by 3n. Denominator has small n here. Small n tends to infinity. This ratio reaches to infinity. The n value reaches to infinity. This ratio reaches to 0. Therefore, 2x bar minus 1 is consistent estimator of Kaplan. Alternatively, we can also use Chebyshev inequality, and also you have to identify the consistent estimator of the unknown population parameter. So, but this is apply the sufficient condition for consistency is very simple one here. So, this sufficient condition for consistency already includes the unbiased estimator property. So, additionally, you have to calculate the variance here. So, to calculation of the mean and variance are very important for the very important concepts for the each and every point of view. So, example 3. X follows continuous uniform distribution. X follows letter. X follows uniform distribution A comma B. Now here is this is a population. The population distribution is continuous uniform distribution. Parameters A and B. Here is A is known. A is known. Now consistent estimator of B dash. consistent estimator of B dash. Consistent estimator of B dash. Now, first you have to calculate the expectation of X is equal to mean of this continuous uniform distribution. Mean is equal to B plus A by 2 implies expectation of 2x is equal to B plus A. A is a constant value. Now expectation of 2x minus A is equal to B. 2x minus A is equal to B. A is a constant value. Now let x1, x2 and so on xn be a random sample drawn from the uniform distribution. Now identify the function of sample observations, that is called x bar. X bar is equal to B plus A by 2. So now here is expectation of Px bar minus A is equal to B. Px bar minus A is unbiased estimator of B. Now variance of x bar, the formula is sigma square by n. Now variance of x bar is equal to, for variance of uniform distribution is variance of x is B minus A whole square by 12, that is variance of x. It is denoted as sigma square. Thumb rule, variance of x bar. So variance of x bar means variance of sampling distribution of statistics x bar, sigma square by n is formula. Substitute here, sigma square is equal to B minus A whole square by 12n. But our requirement is variance of Qx bar minus A. Now apply the variance property. 4 into variance of x bar. Variance of constant is 0. 4 into variance of x bar. B minus A whole square by 12n. That is equal to B minus A whole square by 3n. Now apply the sufficient condition for consistency. Apply the sufficient conditions for consistency. Limit n tends to infinity. Expectation of Px bar minus A is independent of n. So this value limit n tends to infinity. N tends to infinity. 2x bar minus A is equal to what here? B. Limit of B is what? B. Constant. Limit of constant is constant. Second one, limit n tends to infinity. Variance of 2x bar minus A is equal to limit n tends to infinity. B minus A whole square by 3n. As n tends to infinity, this value is equal to 0. Therefore, Px bar minus A is consistent estimator of B. Consistent estimator of B. Problem 4. Let xi follows Bernoulli 1 comma p. Here IIDs, xi's are IIDs. I is equal to 1 to n. Our requirement is consistent estimator of p dash. Consistent estimator of p dash. Now, here is let x1, x2, xn be a random sample drawn from this Bernoulli population. The parameter is p. We have to identify which one is the consistent estimator of p here by applying the sufficient condition for consistency. First of all, E of xi is equal to p. Variance of xi is equal to p into 1 minus p. Pq. Q means replace q by 1 minus p. E of x bar is equal to p. Variance of x bar is equal to this variance of xi denoted as sigma square. Formula is sigma square by n. So now this is p into 1 minus p by n. By applying sufficient condition for consistency. So first one, as n tends to infinity, expectation of x bar tends to p. Second one, as n tends to infinity, variance of x bar tends to 0. That is limit of n tends to infinity, p into 1 minus p by n. This tends to 0. Therefore, x bar is consistent estimator of p of Bernoulli population. Example 5. One more example. Let xi follows Poisson lambda. I is equal to 1 to 1 so on n. The consistent estimator of lambda dash. Xi follows Poisson lambda. IIDs, finite number of sample observations. I is equal to 1 to n. Now here, consistent estimator of lambda. First of all, mean and variance. Lambda is same as to variance of xi. So now E of x bar is equal to same as to E of x lambda. Variance of x bar is equal to sigma square by n. Sigma square is equal to lambda by n. By applying this condition as n tends to infinity, expectation of x bar tends to lambda. Second one, as n tends to infinity, variance of x bar tends to 0. Limit n tends to infinity, lambda by n. So here n reaches to infinity, the lambda by n reaches to 0. Therefore, x bar is consistent estimator of lambda. Six. Let xi follows C of 1 comma mu, Cauchy population, one parameter case. Scale parameter is 1, location parameter is mu. Kashi population mean does not exist directly. Consistent estimator of mu is here. Kashi is a special probability distribution. Kashi is a special distribution. Kashi mean does not exist. Higher order moments also does not exist. MGF does not exist. Now, here the sample mean is not consistent estimator of population mean mu. In this case, alternatively, we have take sample median. Sample median is a consistent estimate. We have to show that sample median is a consistent estimate of the population parameter mu. Is very, very important from the examination point of view. Now, by taking principal value of U of x is equal to U of xi, IID is mu. Variance of xi does not exist. Does not exist. Expectation of function of sample observations U of x bar is equal to mu. Variance of x bar does not exist. Does not exist. Therefore, we cannot apply the sufficient condition for consistency. So in this case, x bar is not consistent estimator of mu. But in this case, additionally, we have to take the median. The sample median is also unbiased estimator of population mean mu. Expectation of MD is equal to mu. Both are the unbiased estimators. So variance of MD. So variance of MD using systematic procedure. Variance of MD pi square by 4n. By applying this one, apply the sufficient conditions for consistency as n tends to infinity, expectation of median tends to mu. Second one, limit n tends to infinity, variance of median is equal to limit n tends to infinity, variance of median is equal to pi square by 4n. By n reaches to infinity, this ratio reaches to 0. Therefore, the sample median MD is consistent estimator of consistent estimator of mu, consistent estimator of mu for Cauchy population, for Cauchy population. So here is very, very important. For Cauchy population, sample mean is not consistent estimator. Sample median is a consistent estimator of mu. This is very, very important. So bit for the examination point of view. I am giving one more example. We are going to discuss about the one more example. That is let xi follows exponential 1 by theta. Here I is equal to 1 to n. The consistent estimator of theta dash. The consistent estimator of theta dash. So E of xi is equal to exponential mean. Parameter is 1 by theta. Mean is theta. Variance of xi is equal to theta square. You know very well, E of x bar is equal to same of E of xi. You have a formula, variance of x bar is equal to sigma square by n. This is equal to sigma square theta square by n. As n tends to infinity, by applying the sufficient condition for consistency, as n tends to infinity, limit of n tends to infinity, E of x bar is equal to limit of n tends to infinity, theta, this is equal to theta. Limit of constant is constant. Second one, second condition, limit of n tends to infinity, variance of x bar is equal to limit n tends to infinity, theta square by n. This tends to 0. Therefore, x bar is consistent estimator for theta. Consistent estimator for theta. One more example. Let x1, x2, and so on xn are random sample from Bernoulli distribution with parameter p. Dash is the consistent estimator of p into 1 minus p. Very, very important one. Is a direct question. First here, xi follows Bernoulli 1 comma p. Let T is equal to the function of sample observations. To identify the unbiased estimator or consistent estimator or efficient estimator or sufficient estimator, first of all, we have to think about the function of sample observation. Which function of sample observation is suitable to estimate the unknown population parameter beta? So that's why here always you have to try to identify the functions of sample observations. Is a random variable, is a statistic. So T is equal to summation xi is a suitable one here because we have a L2 property. So this sum of Bernoulli's follows binomial distribution n comma p. Immediately we can write the statistical constant expectation of T is equal to NP. So variance of T is equal to NP into 1 minus P. Easily we can put this one. So expectation of x bar is equal to the x bar formula expectation of summation xi by n, that is equal to expectation of small t by n. Small t is called summation xi. So 1 by n expectation of t. Expectation of t is already defined here np. So 1 by n into np, that is equal to p. Expectation of x bar is equal to p. X bar is an unbiased estimator of p. So similarly, variance of x bar. So variance of 1 by n summation xi, that is equal to variance of t by n. So now here is the variance of ax equal to a square into variance of x. 1 by n square into variance of t. So 1 by n square into variance of t is equal to n into p into 1 minus p. So simplified format, variance of x bar is equal to, after simplification, here n square cancel. That is p into 1 minus p by n. Apply the sufficient conditions for consistency. Expectation of x bar tends to p as n tends to infinity. As n tends to infinity. Second one, limit n tends to infinity. Variance of x bar is equal to limit n tends to infinity p into 1 minus p by n tends to 0. Therefore, x bar is a consistent estimator of p. Our requirement is dash is the consistent estimator of p into 1 minus p. So now here p into 1 minus p is a continuous function by invariance property. By invariance property, already explained, go through the invariance property. So now x bar into 1 minus x bar is simply consistent estimator of p into 1 minus p. X bar into 1 minus x bar is a consistent estimator of p into 1 minus p. So this is a very, very important example for the examination point of view. Replace x bar by summation xi by n. 1 minus summation xi by n is a consistent estimator of p into 1 minus p. The last one, let xi follows geometric p. I is equal to 1 to also on n. Consistent estimator of 1 by p dash. E of x equal to E of x equal to 1 by p. Variance of x equal to q by p square. Now E of x bar is equal to same as to E of x 1 by p. E of x bar formula mu. Variance of x bar is equal to sigma square by n. This is sigma square. Q by n p square. As n tends to infinity, E of x bar tends to 1 by p, independent of n. As n tends to infinity, variance of x bar tends to 0. Limit n tends to infinity, q by np square tends to 0. Therefore, x bar is consistent estimator of 1 by p. Several examples are noted. So very important concept, consistent estimator. So we have an alternative advanced technique also available in this theory of estimation. I will give the one more method to identify the consistent estimators of the population, unknown population parameter data. Next, go to the another very important one, efficiency. So efficiency is very important one. So first of all, that statistics T1, T2 are consistent estimators of a certain population parameter theta. Certain population parameter theta, variance of T1 less than or equal to variance of T2. Comparing these two variances of these consistent estimators, both are unbiased estimators. First of all, T1, T2 must be consistent estimators. So here, first of all, check that these T1, T2 are consistent estimators. After that, calculate the variance of T1 and variance of T2. Compare these two one. Which one is lesser? The corresponding statistics is called the most efficient estimator. Most efficient estimator compared to the other estimators. For all in cases, T1 is the most efficient estimator because variance of the T1 has less variance compared to T2. So to identify the efficiency, definitely at least two or more estimators are required to give the efficiency of the estimator of efficiency of the main estimator compared with the other estimators. T1 is the more efficient estimator than T2 for all samples of sizes here. Thus, sample size is finite. Here is remarks here. T1 is the most efficient estimator with variance V1 and T2 is any other estimator with variance V2. Then the efficiency E of T2. So here calculate the efficiency of T2 compared with T1 here. So now which one is more efficient estimator? So that is the numerator value. Which one is the less efficient estimator? That is the denominator value. So defined as here V1 by V2 here. Using this formula, we can able to measure the efficiency of T2 estimator. So compare with T1 estimators. That E efficiency denoted by E is always less than 1, cannot exceed 1 here. So suppose E is less than 1, so implies variance V1 less than V2. So we can say that V1 is the variance of T1, V2 is the variance of T2. So T1 is the most efficient estimator. Suppose several estimators are there. T is the main estimator, T1, T2, T are sub-estimators, are all estimators of G of theta here. So using this capital T, capital T1, capital T2, capital Tn, so we can able to estimate the G of theta. All are consistent estimators, are all unbiased estimators, but need not be unbiased estimators. But all estimators must be consistent estimators. After that, we can examine the efficiency of the statistic. Now, in this case, in this sequence, variance of T has minimum here. So that's why T is the most efficient estimator. In this case, the formula is the efficiency denoted by EI. EI is equal to variance of T by variance of TI. So TI is the I is equal to 1 PN. So the efficiency of T2, the efficiency of T1, to calculate the efficiency of T1, efficiency of T2. So using this formula here, suppose efficiency of T1. That is equal to formula is variance of T by variance of T1. To calculate the efficiency of T2, in this case here variance of T by variance of T2, because variance of T has minimum variance. This is the most efficient estimators. To calculate the efficiency of other estimators, so using the most efficient estimators. So similarly, you have to calculate the remaining En is equal to variance of T by variance of Tn. Next one, in the normal samples, since sample mean x bar is the most efficient estimator of U, the efficiency of E of median for such samples is for n is large case. So variance of x bar you know very well, that is sigma square by n. The variance of median already, so here is pi sigma square by 2n for large case here. Pi sigma square by 2n for normal population. For normal population, the variance of x bar is sigma square by n, variance of median pi sigma square by 2n. This is an advanced concept here for degree. So based on the degree syllabus, no need to calculate here. Define the variance of median. So this is a sampling distribution of a sample statistics median case. That mean is equal to expectation of median is equal to mu, but variance of median is equal to pi sigma square by 10. Now we have to examine the efficiency of median compared with x bar. X bar is the most efficient estimator. So now here variance of x bar by variance of median pi sigma square by n by pi sigma square by 2n. After simplification, this is 2 by 5. This value is equal to 0.637. This is the efficiency of median compared with mean. So in terms of percentage, 63.7. 63.7% efficiency. This is the efficiency of median. For example, so x bar has 100 marks, the median has 63.7 marks. This is simple understanding purpose of the comparison of which one is best here. X bar has 100 marks, median has 63.7. This is the efficiency of the median compared with mean. So now variance of x bar, so less than variance of median. So we can say that sample mean is the most efficient estimator compared with median. So T is the minimum variance unbiased estimator of g of theta. M means minimum variance unbiased estimator of g of theta. Expectation of T is equal to g of theta, and variance of T less than or equal to variance of T dash. T dash is any other unbiased estimator of g of theta. So now here these two conditions satisfied. First of all, unbiasedness. This one is minimum variance. These two satisfied. So the T is called minimum variance unbiased estimators. This is very, very important topic for the examination point of view. So example, I am taking one example for understanding purpose of the efficiency. Example 1. Let x1, x2, xn, xn, x5, 5 samples are drawn here from x1, x2, xn, 5 samples drawn from the normal population with unknown mean mu, and variance sigma square. Let T1 is equal to summation xi by 5. Another statistics T2 is equal to x1 plus x2 by 2 plus x3. So another statistics 3, 2x1 plus x2 plus lambda x3 by 3. Lambda is a constant value. T3 is unbiased estimator of mu. T3 is unbiased estimator of mu. So here we have to, first of all, we choose statistics is unbiased estimator of population mean mu. So now this is the procedure. First of all, calculate E of T1, expectation of T1, expectation of summation xi by 5, that is equal to 1 by 5, summation E of xi 1 by 5, summation I is equal to 1 to 5, E of xi is equal to mu. Here is already is given in the problem. E of xi is equal to mu. Variance of xi is equal to sigma square. Now this is equal to 5 mu by 5. 5 cancel. Expectation of T1 is equal to mu. T1 is unbiased estimator of mu. T1 is unbiased estimator of mu. Next, expectation of T2. Let's check the statistics. T2 is unbiased estimate or not. X1 plus x2 by 2 plus x3 by applying properties. Expectation of x1 plus x2 by 2 plus expectation of x3, that is equal to 1 by 2 mu plus mu plus mu. Mu plus mu is equal to 2 mu by 2 plus mu, that is equal to 2 mu. Expectation of T2 is equal to 2 mu, not equal to mu. Therefore, T2 is not unbiased estimator of mu. So expectation of T3 is unbiased estimator of mu. So now we have to find the lambda value. Expectation of 2x1 plus x2 plus lambda x3 by 3 is equal to mu. Is given in the problem. 1 by 3 constant. 2 into expectation of x1 is mu. Expectation of x2 is equal to mu. Lambda expectation of x3 is equal to mu. Is equal to mu. Mu is a common factor for both sides. So now here is 1 by 3 mu taken outside. 2 plus 1 plus lambda. That is equal to mu. Mu cancel. So now lambda plus 3 by 3 is equal to 1. Lambda is equal to lambda plus 3 is equal to 3. So therefore, lambda is equal to 0. After that, so we have to examine the which one is most tested estimate. T1, T2, T3. Now T1 is equal to summation xi by 5. T2 is equal to x1 plus x2 by 2 plus x3. T3 is equal to, by substituting lambda value 0, 2x1 plus x2 by 3. This one, which one is most efficient estimator? And also calculate the relative efficiency of T1, T2, T3. First of all, here variance of T1. Variance of T1. Variance of summation xi by 5. That is equal to 1 by 25. Summation variance of xi. So 1 by 25. Summation I is equal to 1 to 5. sigma square. Variance of T1 is equal to 1 by 25 5 sigma square. Sigma square by 5. That is variance of T1. Now variance of T2 is equal to variance of x1 plus x2 by 2 plus x3. x1, x2, x3 are independent. Now here is 1 by 4, applying the variance properties. Variance of x1 plus variance of x2 plus variance of x3. Variance of T2 is equal to 1 by 4 sigma square plus sigma square plus sigma square. 2 sigma square by 4 plus sigma square. Here is cancel 3 by 2 sigma square. Now variance of T3. Variance of 2x1 plus x2 by 3. That is equal to 1 by 9. 4 variance of x plus variance of x2. Variance of T3 is equal to 1 by 9. 4 sigma square plus sigma square. 5 sigma square by 9. Now comparing variance of T1. Variance of T1 is equal to sigma square by 5. That is 0.2 sigma square. Variance of T2 1.5 sigma square. Variance of T3 0.55 sigma square. Comparing the coefficients, which one is less? Which one is less? 0.2 sigma square is greater than, less than 0.55 sigma square less than 1.5 sigma square. This is variance of T1 less than variance of T3 less than variance of T2. Therefore, minimum variance V of T1 is equal to sigma square by 5. So actually this is the original process here, but examination point of view, no need to take this process here. So X bar is always most efficient estimator compared to any other estimate. So T1 is equal to X bar, sum of observations by number of observations. T1 is most efficient estimator for mu here. So no need to take all these procedures. Directly you can go to this one here. And our statistics is same as to sample mean. Definitely the sample mean is the most efficient estimator for mu here. Now, efficiency of T2. I am very much interested to calculate the efficiency of T2. So T1 is already defined here, most efficient estimator. Compare T2 with the T1 here. In this case, variance of T1 by variance of T2. So here we are calculating the efficiency of T2. That variance must be in the denominator value. So numerator has the most efficient estimator variance. Denominator has the any other estimators. Variance of T1 is equal to sigma square by 5. Variance of T2 is equal to 3 by 2 sigma square. Now sigma square by 5 into 2 by 3 sigma square is cancelled. That is equal to 2 by 15. That is the efficiency. Is less than 1 here. Similarly, efficiency of T3. Variance of T1 by variance of T3. Sigma square by 5 by 9 sigma square is cancelled here. 1 by 5 into 9 by 5. That is 9 by 25 less than 1. That is the efficiency of T3 compared with T1. So today in this video lesson, consistency and efficiency concepts, properties of theory of estimation explained. Several examples are explained